All right, we're going to finish chapter 20 today. Last time we left off with expected radioactive decays. All right, so if you have a high mass isotope versus a low mass isotope, you will do different things here. So we'll go back to, say, carbon 14, one that's easily remembered. Carbon is a mass of 12. So 14 is higher than the periodic table's 12, so you have a high mass. All right, and so when you have a high mass, you're going to do a beta emission, and so you can put it as E, or you can put it as beta. All right, but the numbers are 0 and -1. All right, now you have on top, you have 14 on the left, so you have to have 14 on the right. On the bottom, you have a 6. Here is a -1. You have to have 7 minus 1 to equal 6. And then you look at the periodic table and you see you have nitrogen. You look at the mass of nitrogen on the periodic table, it is 14. So it's going to a more stable isotope. That's why things do radioactive decay. They are decaying to something that is more stable. The other choice would be a low mass. So I pick carbon 11. All right, so again, on the periodic table, it's carbon 12. So here you can do two things, and they will give you the same product. A positron emission or an electron capture will give you the same product. All right, so if we do a positron emission, that is a positive electron. So you can put E or you can put beta. All right, but this time on top we have 11. On bottom we have 6. Here we have a 1. So you just need a 5. You look at the periodic table, and element number 5, atomic number 5, is boron. And if you look at boron's molar mass on the periodic table, it is 10.8-ish. All right, so it's very close to 11. So you have a more stable isotope. If you don't believe that an electron capture would give the same thing, I can write it as an electron capture. Now, capture means you are a reactant, 0 and -1. And so again, on top you have 11. On bottom you have 6 minus 1. That's 5. All right, so either way, you get a boron 11. So a positron emission or an electron capture. If you have a low mass isotope, so these will be for low mass. And how do we know if it's low mass? You look at the periodic table, you see the molar mass of the atom in question, and then you'll look at the number they gave you. It's either going to be smaller than that or higher than that. If it is higher than that, then here it is a large mass. So higher than the molar mass given on the periodic table. Then you would do a beta emission. All right, so your calcium here, if you look, calcium is 40, not 47. All right, so periodic table, calcium is going to be about 40 grams per mole on the periodic table. So this is a high mass. All right, so now you're going to do a beta emission. All right, and so then you have a 47 and you have 21. I don't have a periodic table with me, so we're going to see what element number 21 is. I have a guess, but I'm not going to guess it. No, they don't give it. They just said it, give the type of radioactive decay, not to write the reaction. So since it's a high mass, you do a beta emission. So all you have to do is look on the periodic table. I want to say it's SC, but I'm not going to guess there. So I won't. But all you got to do is get a periodic table, look for element 21, and write the symbol right there. All right, there won't be any radioactive decay series problems on the test, so I'm just going to skip through that. All right. All right, so you have different types of water. You can have the regular hydrogen. You can have another one that is a 3-1. All right, so you have a tritium. So with hydrogen, there are 3 isotopes of hydrogen. All right, except H11 is 99% of hydrogen. All right, but you can have H21, which is called deuterium. All right, so that's a very common isotope that is used for a lot of different, when you label things, you can label it with a deuterium and you can detect where that deuterium went on your compound. Or tritium, which is pretty much used for nuclear chemistry and not very much practical chemistry, regular chemistry, chemical reactions. It is mostly just used in nuclear chemistry. All right, so a deuce, two, deuterium, tricycle, three wheels, tritium. Okay, so that's the mass. So regular hydrogen or a proton. All right, so then you have deuterium and tritium. So you should be familiar with the isotopes of hydrogen. All right. So the questions, which molecule has more mass? Of course, the one that has the 3-1, which means it has 2 extra neutrons. And of course, H1 proton, very stable. So deuterium or tritium would be much more radioactive. All right, so we will be doing transmutation. We're going to hit a nucleus with a particle, and we're going to kick out another particle and get another nucleus. All right, so in this example, we take a nitrogen-14 and we bombard it with alpha particles. All right, so you have to remember that the helium is alpha. The helium nucleus is an alpha. You also have to remember that an H11 is a proton. All right, so this is where we bombard our nitrogen-14 with a helium, an alpha particle, helium nucleus, and then it has to give you one of the products. So there can only be one unknown in this problem. Cannot be two unknowns. All right, so you have your, so usually they will leave out this, but they can leave out anything they want. Your target is your nitrogen-14. You hit it with your alpha particles. You kick out a proton, and what else? All right, so you got your top numbers, 14 and 4. On this side, it would have been a 1. So this has to be a 17 in order to be 18 on both sides. On bottom, you got your 7 and your 2. You got your 9. Proton has a 1. You need an 8 here. You go to the periodic table. You find that atomic number 8 is oxygen. And so you're going to write this in a shorthand form. So you have your target, nitrogen, 14, 7, and then you have the incoming particle, which is an alpha. It's always given as its symbol, not as an He42, always the symbol. The exiting particle, proton, again, not H11, the symbol for that, P. And then usually the question is a question mark here. All right, so we have figured that out, that would be an oxygen 17,8. And so that is your product nucleus. All right, so this is the notation that you're going to have to know how to do for these reactions. So you have to know the symbols for all of your different particles, and you have to know the numbers that go along with them. Highly recommend flashcards. Make sure you know what a alpha particle is, a proton, a deuteron, etc., etc. All right, so here we have a beryllium 9,4, so you would have a Be 9 and 4. Then you have the incoming particle, which is the alpha particle. You would have the exiting particle, the neutron. All right, so then it's just a matter of get the numbers on top, the same on both sides. So a 9 and a 4 is 13. If you were given a neutron, you have to know a neutron is 1 neutron, 0 protons. So it's 1, 0. And so you have a 12 to get 13 on top. On bottom, you got a 4 and a 2. Neutron has a 0 here. That's a 6. And so now you know your product nucleus is a carbon-12. And so you would just write carbon-12, 6. Again, the bottom number is optional. All right, you don't have to put carbon with a 6. Everyone can just look at the periodic table and find carbon and see that it's 6 in your notation. When you're writing out the reaction, you must put the numbers. When you're doing it in a shorthand form, you would not have to put the numbers on bottom. You must put the numbers on top because they're different isotopes. But carbon is always 6, but carbon is not always 12. It is 13, it is 14. All right, beryllium is always 4, it's not always 9. All right, so you have to put the number on top because that is a number that could be different. All right, so here we have aluminum, 27, 13. Again, incoming particle alpha, exiting particle a neutron, and then you get a phosphorus, 30 and 15. So again, you're going to be given, let's say you're given the first 3. You have to come up with the last one. All right, so we have on top 27 and 4, which is 31. We have 30 here. That has to be a 1. On bottom, we have 15. On bottom, we have 15. That one has to be a 0. So you have to know that a 1, 0 is a neutron. All right. This is not a nuclear bombardment. There is not something coming in. This is simply a decay mode. All right, so this is you have to know what this is called. That is a positron. That is a positron emission. All right, anytime it's a product, it is an emission. If it is a reactant, it is a capture. And so then they go through the abbreviated forms, all right? So you have to know what the symbol, you have to know N is a neutron, P is a proton, D is a deuteron. So that is a 2, 1. Tritiron, that is a H3, 1, and that is a T. So if you have a T, lowercase t, as a particle, that is a tritiron, an H3, 1. All right, there's probably more. We got the alpha. I didn't put beta here. Okay, of course, a beta. I guess the ones they already did, they don't put up. Beta is a 0, -1, which is the same as an electron. Positron. So you have to know a positron. All right, what they're going to put for positron is a beta plus. They could put an E plus, but that's rare. Or I guess you could put E plus. But it's usually a positron is a beta with a plus charge, right? So that is an beta with a 0 and a 1, or an E with a 0 and a 1. So you have to know the symbols for all of your different particles that we talk about. And of course, your gamma is a 0, 0. So gamma is 0, 0. It's pure energy. So that is a gamma particle. So you have to know your symbols for your particle. All right. Write the abbreviated notation. So we already did this. So this is your Be9, then your alpha, then your neutron, then your carbon 12-6. All right. So they could give it this way and say, write the balanced reaction. So here's where you have to know your numbers. So Al 2713, they have to give you the 27. They don't have to give you the 13. You have a periodic table. Proton, so you have to have it. You have to know immediately that a proton is a H11, or if you put P11, that's fine as well. All right, but you have to have the 1, 1. That is the key. And then a deuterium, so that is an H21. You could put D21 if you want. I wouldn't count that wrong. All right, and then you have plus. And then normally they have this omitted and you have to come up with it. And you would say, I have 27 and 1, I have 28. Here I have 2, this has to be a 26. Here I have 13 and 1, I have 14. Here I have a 1, I have 13 again. And then I look at the periodic table and 13 is aluminum. You must know the hard part about this. It's very simple. If you know what the particles represent, then it's simply, can you add numbers on both sides and make them the same? All right, so a cyclotron, that's a particle accelerator. So we're going to bombard something. We got to get it going very fast, and we're going to hit our target. And so a cyclotron is what gives that particle its energy in order to get in there and break apart your nucleus. Right. Transuranium, if you hear the term transuranium, that just means elements after uranium. All right, so that is, uranium is atomic number 92. So any elements past 92 are called transuranium elements. All right, and all of these are made in labs by doing different nuclear reactions. All right. So uranium-238 plus a neutron will have uranium-239. And then uranium-239 will then do a beta emission. That should be called a beta emission. All right. And that would give neptunium. All right. So here is that is just a neutron capture. And this is just a beta emission. So these are just radioactive decay modes. All right. Whereas, but you have to somehow get the neutron in there. You got to put the neutron in, either by a cyclotron or whatever you have to react it with the uranium-238. Here is our transmutation. So here we have a uranium-238, 92. We hit it with a deuterium, D, that is a 21H. Oh, well, but this is not going to be that way because whenever you're doing a transmutation, it's only going to be one particle released. So this would not have, you don't have two neutrons here. It would have to be one. So this is something where you would just have to write it out. Now here, instead of writing 2, which can confuse people, you may want to just say 1, 0, N, 1, 0. You might want to write it twice because the 2, sometimes people don't put the 2 here, or if there's a number down here, they don't do the 2 there. So if you see 2 neutrons, you may want to write it out 2 times. So to see that we have a 238 plus 2, we have a 240 on top, and then you have a 238 and 2 neutrons. So 1 there, so you got 240 on top. On bottom, you got your 92 plus 1, so that's 93. On bottom, you got your 93 and your 2 zeros. You got 93. All right, so you have to have a balanced number on top, same number of protons and neutrons, and on bottom. All right, and so here is just another beta emission. Again, the numbers on top, 238. Yes, 238, 93, 94, and the -1. Make sure the -1 will catch people and get them wrong. Okay, it's a -1, so 94 -1, 93. All right, so these should be very simple to balance. All right, so here is a plutonium-239 bombarded by alpha particles, helium-42. Each plutonium nucleus was struck by one alpha particle and emitted one neutron. All right, so this is a transmutation. And what was the product nucleus? All right, so you have your plutonium-239. All right, so, and you hit it with an alpha particle and you got a neutron. Again, this is a very simple question. You just have to have the numbers on top and bottom be the same. So here we have a 243. All right, you have a calculator if you don't like to add. This is 243. This is 1. So, of course, you need 242 plus 1 to equal 243. Again, this is very simple second grade math. All right, you got 94, you got 2. That is a 96. You got a 0. Obviously, this has to be 96 because 96 plus 0 is 96. So 242, 96. And then you look at the periodic table, you get what atomic number 96 is, and you see that that is Cm, and then you write the nucleus. All right, so this is I think that's how they started the question, so maybe not. Pu 238, they don't have to give you the 94, you have a periodic table. Then alpha, then neutron, and then your final answer was the question, Cm 24296. So that's how you would write it in its notated form. Again, these questions should be quite simple. All right. All right, so now we're going to get into radioactive decay. The good news is that all radioactive decay is first order. So this is all first order. So these, you don't have to worry, is it first order, is it second order? All of them are first order. All right, so we measure radioactivity. We measure it using a Geiger counter, and we have a unit from named after Marie Curie, who did a lot of work on nuclear chemistry. So it is a 3.7 times 10 to the 10th disintegrations per second. That is a 1 Curie. All right, so that is a constant like Avogadro's number per moles, 12 is a dozen. All right, so that would be given. That is a conversion factor from disintegrations per second to Curies. So you don't have to memorize that number. It would be given. All right, radiation effective dose. This is, if you work in a nuclear facility, they're going to give you a pin. You're going to be monitored every day, week, month. They're going to have all that information. You can have only so much radioactive exposure. We're not going to go through all the radioactive exposures. Right. Well, so your alpha radiation has the highest, so it causes the greatest damage. But the good news is that clothing is all you need to block your alpha radiations. Others need a lot more protection. All right, rate of radioactive decay. So again, it's first order rate law. So rate is equal to K, and then you have your N at time T. So that is the number of radioactive nuclei at time T. So that's how you will get your rate. K is, of course, the rate constant, radioactive decay constant, right? And so that is going to be 1 over time. All right, so your K, well, remember the K units for first order was 1 over seconds. All right, but some of these have half-lives of years and years and years, so it doesn't have to be seconds. Any measure of time. Because many times our units are going to be 1 over years because these things have half-lives of many, many years. But some of the ones that are used in medicine have very short half-lives because we don't want them to be in our system forever. We want them to go down to a very low concentration very quickly. All right, a 10 milligram sample of technetium-99 has an activity of 1.7 times 10 to the minus 5 Curies, decaying by beta emission. All right, and so we have a beta emission. So you got your TC 9943 undergoing beta emission. So you have to know that's 0 and minus 1. So we're getting 99 and we're getting 44. So make sure you don't ignore the negative because 44, this is minus 1, 43. All right, so then you look on the periodic table and you could find what that element is. All right, so your rate of decay, so you put in your rate. That was 1.7 times 10 to the minus 5 Curies. Now we have our conversion factor. So this is nuclei per second. All right, so this is 3.7 times 10 to the 10th disintegrations per second per Curie. So we are canceling out our Curies, and now we are getting the number of nuclei that are undergoing this reaction per second. All right, so the number of nuclei in a 1 times 10 to the minus 3 gram sample or 1 milligram sample. So now we have our grams, we're going to convert it to moles. Technetium-99 will have a molar mass of 99. So that is 99 grams per mole. So this gives us the moles of technetium. Well, there's Avogadro's number of nuclei in a mole. And so we multiply that by Avogadro's number. So that's the number of nuclei we get. So here is your nuclei, and here are your nuclei per second. All right, so then your decay constant, so remember your rate is equal to K N sub T. All right, and so the decay constant, we are solving for K, and we know it's going to be 1 over time because all of our reactions for nuclear chemistry are first order. So we take the rate, which was 6.3 times 10 to the 5th nuclei disintegrations per second. All right, divide that by, because we solved for K, so we divided both sides by the number of nuclei at that time. All right, so we had the mass, we converted the mass to moles, we converted the moles to nuclei using Avogadro's number, and we have 6.1 times 10 to the 18th. So when you divide those two numbers, you get K, and note it is per second, 1.0 times 10 to the minus 13 per second. So the units for K will always be 1 over time. All right, and also remember for first order, the half-life equation, there's only one to know. We're not going to use any second order. It's all first order in this chapter. 0.693 over K, that is our first order half-life. So we simply put our K value in, and we can solve for our T1 half. So we put in 0.693 divided by 1.0 times 10 to the minus 13. And that's going to give us 6.93 times 10 to the 12th seconds. All right, so you take your 0.693 and divide by the 1 times 10 to the minus 13. Yes, and now that's seconds. If you wanted hours, there's 3,600 seconds in an hour. All right, so that is a lot of hours. So you keep going, 24 hours in a day, divide by 24. That is a lot of days. And then we're going to go with 365 days in 1 year. So then you divide by 365, and that's where we're going to get our answer. And that is, sig figs, just 2.2 times 10 to the 1, 2, 3, 4, 5. That's a 5 years. All right, so that is 220,000 years. All right, so that's how many years it would take for half of those to decompose. So that is and you're going to see that a lot for these nuclear reactions. They're going to have very large half-lives. And that's the problem with our nuclear waste. They do not decompose very fast. They're going to be here for hundreds of thousands of years, and that's only when half of it's gone. So we still have half of it at that point. All right. Okay, so now they're doing it in years. All right, so 2.2 times 10 to the 5th years. So that is a very large half-life. All right, so tritium is a radioactive nucleus of hydrogen. All right. Half-life, 12.3 years. So now we know that the T1 half, it's always 0.693 over K, because it's always first order. But now they gave us the half-life. So the half-life is 12.3 years. And that's equal to 0.693 over K. So you could easily solve for the rate constant K. So you take your you take 0.693, divide both sides by 12.3, multiply both sides by K. So you got 0.693 divided by 12.3, and that will give you your K value. All right, so your rate constant K for this process is 0.0563. And that is in 1 over years. All right, so we know the K is 1 over time. All right, and this one I used years for my 12.3, so my K is going to be 1 over years. What is the decay constant in seconds? All right, so that's kind of a big pain. Now you got to go to seconds. So 1 over seconds. We have 1 over years. So the easier way to do it is to take the 12.3 years, and before you stick it into this equation, put it in seconds. You can do it a different way. This is the way that you have less errors. 365 days in a year. You have your 24 hours in a day. All right, so again, years are canceling, days are canceling. You got 24 hours in a day, so you got 60 minutes in an hour. Hours cancel. All right, and you've got 60 seconds in a minute. And so you just simply multiply your 12.3 by 365, 24, 60, and 60. And then you have your answer in seconds. Then you take your K value is 0.693 divided by T1 half. So if you put in your T1 half in seconds, then you have the answer that they want. All right, so then it says, what is the activity of a sample containing 2.5 micrograms of tritium? All right, so activity is the rate. And so here you have rate is equal to K and T. All right, so K, we just found K. All right, so it asked for it in 1 over seconds. If it didn't say, I would leave my K right there. All right, 1 over seconds, then you have to do it this way. All right, and so you will have your K value in 1 over seconds, and then you have to find the number of nuclei in 2.5 micrograms of tritium. Your 2.5 micrograms, you have to know micro is times 10 to the minus 6 grams. You convert that to moles. It is tritium. You have to know tritium is 3,1. And so the molar mass is 3 grams per mole. All right, so now you have moles, and now you have 6.022 times 10 to the 23rd nuclei per mole. And so that, when you multiply that out, that is your number of nuclei at time t. All right, so they will do all this for us with all of the units here. All right, so you got your 3.88 times 10 to the 8th seconds. That is your time. We converted our time by multiplying all these. All right, so that is our half-life. And so we have our K is equal to 0.693 divided by the T1 half. We're just going to plug that number in, get our K value. So when we plug that in, we get our K value, and that is 1.79 times 10 to the minus 9, 1 over seconds. All right, so now that's our K value. So again, we are solving rate is equal to K times N sub T. There is our K value. All right, so now we have to convert our micrograms, 10 to the minus 6 grams. All right, and so your tritium, if you look on the chart, they will have the molar mass of tritium, and it is 3, but 3.02 to keep the 2 sig figs, or just simply 3.0, because we only need 2 sig figs. And instead of using 6.022, you just use 6.02. Again, we're only going to get 2 sig figs. So your micrograms divided by the molar mass of 3 times the number of nuclei per mole. So here is your N sub T, nuclei at time T. 5 times 10 to the 17th. All right, so now we have our K value. So rate is equal to K and at time T. We have our K value. We also have our N at time T value. And then that is going to multiply those together, and that gives us our rate. It asks for activity. Rate is equal to activity. All right, but they asked for our activity in curies. So we have to do a units conversion. Here is our activity, but again, they wanted the units to be curies. So the reason why K had to be in seconds is because a curie is nuclei disintegrations per second. And so we had to get our nuclei per second to cancel our nuclei per second in order to get our curies. All right, and so when you have your constant, 3.7 times 10 to the 10th, nuclei disintegrations per second is 1 curie. And we have our activity of 9.0 times 10 to the 8th, nuclei disintegrating per second. And so we just divide that, and we get our activity in curies. All right, so if we do our integrated rate law back in chapter 13, it was the ln of A at time t over A initial. And that was equal to negative KT. All right, we're doing exactly the same thing, except we're not doing concentration of something at time t. We're doing the number of nuclei at time t versus the number of nuclei that we started with. All right, so the original number of nuclei, the nuclei we started with, number of nuclei at time t, that's n sub t. All right, and this is the fraction of nuclei remaining at time t. When you divide them, you get a fraction. The number that you started with is always larger than the number you have. They are decaying. The number is going down over time. So that is a fraction of nuclei remaining. All right, so phosphorus 32, radioactive isotope, half-life is 14.3 days. If you have a vial of this compound, all right, if the compound is used in an experiment, 5.5 days after the compound was prepared, what fraction of the isotope is present? All right, so here you have your ln of n at time t over n initial. That's equal to negative KT. All right, so what we have to have is the same units for our times in this one. All right, so you have to have your time in days, and your K value has to also be in days, or you can convert everything to seconds, but that's just a lot of extra work. All right, so we have our T1 half is equal to 0.693 over K. To solve for K, well, K, when you multiply both sides by K and divide both sides by T1 half, is 0.693 over T1 half. So to get the K value, take your 0.693 and divide by your 14.3 days. All right, so we have days for our K, 1 over days. And then we also have days for our time. And so you can find the ln of n at time t over n initial by putting those numbers in. So you have your K value without pushing buttons, it's 0.693 over 14.3 days. And then we have 5.5 days later, and we see that days cancel days. So that's the key. You have to have your time units to be the same so that they cancel. All right, so suppose the sample contained 0.28 grams of phosphorus 32. How many grams remained after 5.5 days? So that would be simply taking your fraction and multiplying that fraction by the 0.28 grams. All right, so all you have to do here is then to solve for this, you push your e to the x button. To get rid of the ln, you would push your e to the x button. So we will work this out on this page. All right, so we put in our numbers. All right, so we had our 0.693 divided by 14.3 days. So the days canceled the days. All right, so when you push that, you got the negative because it's negative KT. When you push that, you get your ln of n at time t over n initial to be a negative 0.267. Now you push your e to the x button. And this has to be a fraction, a number less than 1. All right, and so when you push the button, you get a 0.77. So the fraction remaining is 0.77. The percent remaining would be 77%. So if we started with a 0.28, only 0.77, they added another sig fig here, it's point. They don't want that to limit our answer, so you get this number to one more sig fig than you need for your answer. Anyway, 0.28 times the 0.77 or an extra sig fig, 0.766. You see that now you have 0.21 grams. All right, so if you ordered your very expensive radioactive nuclei and then you couldn't do it until 5 days later, 5.5 days later, you don't have 0.28 grams anymore. You have 0.21 grams because it is constantly decaying. All right, and that's how we will determine how old things are. So we did a little of this already. Radioactive dating, we got the age of a jawbone. So you have the half-life of carbon-14 is 5,730 years. For all living materials, you have a constant value for your fraction of carbon-14 to carbon. Once an organism is dead, that fraction is going to decrease into carbon-14. The carbon-14 is going to decompose, and there's no way for more carbon-14 to get in. And so you can determine how old something was by doing radioactive dating on your carbon-14. All right, carbon-14, again, that's a high mass isotope. All right, so that is going to decay by doing a beta emission. All right, so here would be an example. You have a piece of charcoal from a tree killed by a volcanic eruption. All right, it gave 7 disintegrations of carbon-14 nuclei per minute. All right, living material would give 15.3. So you have your ln, n at time t over n initial is equal to negative kt. So now we have that it is 7.0 disintegrations of carbon-14. Initially, it was 15.3. All right, and that is equal to negative kt. All right, so now we need to have one of these answers. The question is, how old is it? All right, so we need to solve for how old it is. So we have to be able to find k. But remember, your t 1/2 is 0.693 over k. Everything is first order. So k is 0.693 over t 1/2. And they gave us the half-life of the carbon-14. And so we have just the one unknown. So we put our 0.693 over 5,730 years. Now, if you're putting that in 5,730 years, the answer that you're getting for t would be in years. All right, so whatever units you're using for your half-life, that's the units you're going to get for your time. So when plug those in, all right, so we have our initial was 15.3. At time t, it is 7.0. Okay, why are they inverting this? All right, so for whatever reason, they inverted it and left off the negative sign. I would not be doing that. All right, so I'm going to use the ln n at time t over n initial, and that's equal to negative kt. What they did is they took the negative to both sides, and when you take the negative of the ln, you can invert your fraction, and there is no reason to do that. All right, but so your answer is going to be the same. They inverted their ln fraction in order to get rid of the negative sign. So I have the ln of my 7.0 divided by my 15.3. That is equal to my K value, which is 0.693, over T1 half. So negative 0.693 over 5,730 years. And then solve for T. And when you solve for T, you will get 6.5 times 10 to the third years. So the volcanic eruption occurred 6,500 years ago. And if you subtract approximately 2,000 or minus 2021, the year it is now, okay, so then you have about 4,500 BC. That's 6,500 years ago. All right. If it's too old, then there's not enough carbon present at all to get an accurate date. So there are other methods to get things, other methods to get how old things are if they're older than 50,000 years old. All right, so in medicine, you're going to have different radioactive tracers. Right, so then they can take an MRI, they can see where things are going. All right, so it is used quite a bit in medicine. In medicine, though, you're going to be limited to things that have half-lives in the hours. Usually, if it's minutes, then you got to make it on site and then use it immediately. So usually you want hours or days. Minutes and seconds usually are too fast of a half-life. It disappears before you get it to you. If you ship it overnight even, you have very little left once it gets there. But they don't want things that have half-lives of hundreds of thousands of years, which means it's going to be in your system forever till you die. All right. And it may kill you. So that death could become sooner. So it's like we want to get things out of the system quickly. All right. Energy of nuclear reactants. Reactions. Okay. So in when we do chemical reactions, we have what is called a conservation of mass. Which is not correct. There is not a conservation of mass. There is a loss of mass, but that loss of mass or gain of mass in an endothermic reaction is extremely small, negligible. We cannot detect that in our labs. It's such a small amount. Now, a nuclear reaction, we're not even kidding ourselves. We can easily solve for the amount of energy, the amount of mass that is gained or lost in a nuclear reaction. And so we convert the energy and the mass in Einstein's equation, E is equal to mc squared. All right, so if you have a change in energy, which we find is our heat of reaction, delta H, so you have a delta H, and that is equal then to mc squared. So when you have this in joules, then your mass has to be in kilograms, and your speed of light is meters per second squared. Of course, a joule is a kilogram meter squared per second squared. So you can calculate if it's exothermic, the amount of mass lost. You can calculate if it's endothermic, the amount of mass gained by Einstein's equation. Now, the amount of mass that is gained and lost in a chemical reaction is so small, it does not change the mass in terms of sig figs. However, in nuclear reactions, the amount of energy is tremendously higher, and so the mass is also tremendously higher, and it is a significant mass. All right. So we will find our heat of reaction, and we will then solve for our mass change. And so by using Einstein's equation. All right, so you're going to be given table 20.3, and this is the mass of all of our elements and particles. All right, now your difference here, note that you have a proton and you have an H11, and I said that a proton is equal to an H11. All right, so these are elements. H11 is an element. Proton is a particle. All right, so an electron, a neutron, a proton, these are particles. All right, so these are particles. This is an element. And of course, if you have H11, so one proton is simply one proton. This is not H plus, this is H. And so this has one proton, has 0 neutrons, but it also has 1 electron. And you will note that the mass difference between here and here is the mass of 1 electron. In order to get the mass of a proton, well, it's already here, so you can just write it down. But if it wasn't there, you would take your H11 and subtract the mass of the 1 electron in order to get the mass of a H11 particle with no electrons. So we're just looking for the mass in the nucleus. We're not looking for the mass of the atom, the mass of the nucleus. So the nucleus does not contain any electrons. So we want the mass that is the nucleus, which just is the protons and the neutrons. All right, so that is true for all of our elements. All of these masses, so this one has 2 protons, so this mass in it has 2 electrons in it. If you wanted the nuclear mass, all right, you would have to subtract the 2 electrons here. Same with your helium. They don't give an alpha particle. Alpha particle is not given. All right, so if it asks for the mass of an alpha particle, that is a helium-4 But this is an element 4 That means it has 2 protons, it has 2 neutrons, and it has 2 electrons. In order to get the mass of a helium particle, you have to subtract the 2 electrons. So here's the mass of 1 electron times 2. So you take your mass of electrons, multiply it by 2, and that will give you the mass of an alpha particle. All right, so calculate the energy change in joules for the following nuclear reaction per mole of deuterium. All right, and so you have what you're going to do is you're going to find your delta M. And that is your mass of products minus mass of reactants. So it's always products minus reactants. All right, and so once we have our change in mass, we will find our energy, calculate the energy change by putting that into our delta E. Our energy change is our delta MC squared. All right, so we find our numbers off of the chart. So nuclear mass of a helium-4, that is a 2, all right, is 4.00260. This is off of table 20.3. All right, but to get the mass of the nuclear mass of a He42, we have to subtract the 2 electrons. All right, and so this is our mass of a helium-4 So that goes right there. This H11, you can do it one of 2 ways. You can take the H11 mass and subtract an electron, or know that this is a proton and just take the mass of the proton. All right, if they would have given the mass of a helium, of a alpha particle instead of helium, or both, you could have just went with the alpha particle, but they didn't. But that is the mass of a helium-4 which is an alpha particle. All right, a 3-2, you have to take the mass of the helium-3 off of the chart, and then again subtract the 2 electrons that are in here. Deuterium, you have to take your deuterium mass and subtract the 1 electron that is in there, and that's going to be how you get all of your masses. The only one that you didn't have to calculate was the proton. That's the only one that came directly off of your table. The others, you have to subtract your electrons. And again, the number of protons is the number of electrons. So if you go back to the chart, if you want to know how many electrons, all right, so here is your number of protons. And okay, so here down are your atoms. All right, so you'd have to subtract 1 electron, 2 electrons, 3 electrons, 4, 5, 6, 7, 8, 24, 26 in order to get the nuclear mass. All right, and so then we're going to have to convert it to mega electron volts. So again, any conversion factors would be given. All right, so when you calculate it, you get a delta M of negative 0.01960 AMU. All right, and so your AMUs, or grams per mole, and so if we wanted, when we get our equation, when we get our delta M, to get delta E, remember that's going to be in joules, which means that your delta M has to be in kilograms. And your C has to be meters per second, which is how it's going to be given to you on your table of constants. But when you solve for this is in grams per mole. You have to convert that into kilograms before you can put it into the equation to find your energy. But you have a negative mass, and so you're going to have a minus delta E. So this is a very exothermic reaction. All right, so anytime your mass is negative, then your delta H, or your change in energy, also is going to be negative, because speed of light is always a positive number. All right, so when you plug that in, again, you had to convert your grams into kilograms. C is going to be given. You square it, and now you have your answer in joules. A kilogram meter squared per second squared is a joule. And so now you have your delta H, or delta E in this case. That is your energy for this reaction. All right, so now we're just going to convert our units. All right, so let's see. We want to do change. Here's our delta M. All right, so this is in grams per mole. And you have 6.022 times 10 to the 23rd. Particles per mole. And so this is going to be grams per particle. And then this is in kilograms. Okay, and then you just convert that to kilograms. And this is again, so we're just taking our mass. I don't use AMU, I use grams per mole. You can use AMU if you want. Then I'm going to divide by Avogadro's number, which is going to be number of particles per mole, and the moles cancel, and that's mass per particle. Again, to put it into our E is equal to mc squared, the mass has to be in kilograms, so you divide that by 1,000 to get it into kilograms. All right, and so the last one we had was in joules per mole. This one is in joules per particle. Not sure why they went through all that hassle. Because all you have to do is take this answer, which is in joules per mole. So you release 1.762, not sure why so many sig figs either, times 10 to the 12 joules per mole. And then you have Avogadro's number, 6.022 times 10 to the 23rd nuclei per mole. All right, so when you do that, you take your 1.762 times 10 to the 12th, and then divide by 6.022 times 10 to the 23rd. That gives you a negative 2.93 times 10 to the minus 12. Yep. All right. So they went through a lot more hassle to get this number than they had to. So you already had your delta E in joules per mole. You just had to divide by 6.022 times 10 to the 23rd nuclei per mole. All right. So now this is in joules per nuclei. The other one was joules per mole. All right, and so now you can convert to joules, your joules into MeVs, mega electron volts. Again, this is a conversion factor, and you will see that you have 1.602 times 10 to minus 13 joules in 1 mega electron volt. All right, and this is per nuclei. And so now you have your negative 18.26 MeVs per nuclei. You could have given it in MeVs per mole. All right, so if you would have taken your first number, that was in joules per mole. This one is in joules per nuclei. All right, so you have to see what units that they're looking for. If you're looking for mega electron volts per mole, you do this with your first answer when it was joules per mole. If you want MeV per nuclei, then you have to use Avogadro's number and get MeV per nuclei. All right. Binding energy and mass defect. So this is when you're going to make a particle out of protons and neutrons. All right. The mass defect of a nucleus is the nucleon minus the atomic mass. All right. So if we do a chart here, what we're going to see is when you have smaller nuclei coming together, that is called fusion. When you have larger nuclei breaking apart, that is called fission. And at the top of your scale here is your most stable nuclei, and that's around mass number 50. So iron 56 is a very high binding energy, a very stable nuclei. All right, so again, if you're doing a fission reaction, you're going to take something big and you're going to break it into smaller parts. All right, so you have a heavy nuclei, it's going to split into smaller nuclei, and it releases energy. It also releases neutrons, multiple neutrons. This is it's going to be a chain reaction. In order to get fission to start, you hit it with a neutron, and then the products are multiple neutrons, which can then keep going. All right, so again, you cannot predict. They have to give you 3 of these, and then you can say, well, how many neutrons? You can calculate 4. They could tell you it's 4, and then they'll say what goes here. Again, there has to be just one thing missing, and again, your numbers on top on both sides have to be the same. Numbers on bottom, both sides have to be the same. So fission, you have to know, is something large, splitting into some two or more things that are smaller, and also is going to release some number of neutrons. All right, so if we are running our nuclear power plant, we have some uranium-235. In order to get this reaction to occur, we bombard it with a high energy neutron. So it comes in and it breaks your uranium nuclei into smaller nuclei. So again, it's not just one reaction. It could go here and give 4 neutrons. It could go here and give 3 neutrons. It could go here and give 2 neutrons. All right, so these are the three possible sets of products. You don't have to memorize the three possible sets of products. I'm going to give you all but one of them. So you will have to then solve for the missing one in order to do this reaction. But you do have to know that it is a fission reaction. All right, we have a big molecule breaking into smaller nuclei. So your large nuclei breaking into smaller nuclei and giving off neutrons. That is a fission reaction. Oh, and then so that is a chain reaction. So you got 4 neutrons that can hit 4 more uranium-235s, and all of these give off a lot of energy. So another thing to know about fission and fusion, they give off a lot of energy. And so then they keep going and going and going. And so you have a chain reaction, and you got to have a way to control this chain reaction, or you're going to have a nuclear meltdown. All right, so again, fusion is when you have two small things coming together. So here we have a deuterium and a tritium coming together to form a helium-42, something larger. Also, a neutron is released. So here is when you have smaller things coming together to form something that is bigger. Right, and so this is the energy of the sun and the stars. They do a fusion reaction. We are unable at this point to do fusion on Earth. The temperatures required for fusion are way too high. We can't get that high of a temperature. But someday we will figure it out, and most likely we will have fusion being done, or maybe not. All right, so you have 2 nuclei coming together to form a bigger nuclei. That is nuclear fusion. All right, so yeah, the nuclear power is great because, well, it doesn't have any carbon that is released. It is bad because now we have all those radioactive products that we don't know what to do with. All right, but the other problem is, of course, if you get this reaction going too fast and it heats up too much and it blows the top off your reactor, which happened in Chernobyl, and now you have people dying of radiation poisoning. And you have abandoned towns because it's still very radioactive. Again, these things have half-lives of hundreds of thousands of years. So there's definitely dangers in nuclear power. The good part of it is it produces a lot of power with very minimal usage of nuclei. But the problem is, what do you do with the leftover nuclei? All right, so you're going to do a fusion reaction. You're going to break your uranium. Again, every time you do this, you get neutrons. All right, multiple neutrons, which then can hit 3 more uraniums in this case. And over here, maybe it only gives off, 3 more. So it's going to react 3 more times. Over here, it gave 2. It's going to react 2 more times. Here, it gave 4. It's going to react 4 more times. So the first one is a lot of energy, and then you have 3 times the amount of energy, and then you have 12 times whatever. It keeps going up and up and up until you have way too much energy, and you would get a nuclear meltdown. All right, so to sustain a chain reaction, you have to have fissionable material, which is uranium-235 is what we use. And then you have to have a certain percent of it. For fission reactions, we just need a 3% uranium-235 in order to, that's our fissionable material, that's for our nuclear power plants. 97%, you got to get it very high percent if you want it to be a bomb. So to get an atomic bomb, you need a much higher percentage of this fissionable material. All right, so in a nuclear fission reactor, you're going to have fuel rods. That contains your uranium-235. You're going to have control rods, okay? They're going to absorb the neutrons. All these neutrons coming off, you have to have some way to control that. So a control rod has a compound in it that will absorb your neutrons, and so your chain reaction does not get out of hand. All right, so here is a picture. You got your reaction occurring here. You got your fuel rods in red. You got your control rods in the brown. Of course, if it gets going too fast, you would lower the control rods. If it's going too slow, you bring them out, but don't bring them all the way out because then if it gets out of control, by the time you put the control rod back in, it's too late. You have to have some water source to cool your reactor and to then boil the steam to turn the turbine to generate the electricity. All right, so then fusion, that is too high of a temperature to be done on Earth at this time. You need at least 100 million degrees Celsius. We are unable to reach that temperature. So that is the energy of the sun and the stars. That is the end of chapter 20.